So hello, welcome to today's seminar. So today we have Violeta Calleja. I don't think she needs an introduction, but she did the PhD here with under the supervision of Sandro Meloni. She came last week to a thesis committee.
Yes.
Sandra and Emily, of course. Studying ecology and even applying ecology to social systems. And today she's going to tell us about, I think, interesting methods, things in ecology. The floor is yours.
Thank you, Juan. Can you hear me, or is just for the audience? For there. Okay, so I will have to raise my voice. Okay, so well, it's a pleasure being here because, as Juan has told you, I did my PhD here 2.5 years now, and since then I have been doing a postdoc at Doñana Biological Station, southern Spain, but just full on ecology and nothing of social interactions. And well, I'm very happy to be here now presenting a seminar. Last time that I was here was during my PhD defense, so now I'm way more calmer, let's say. And I'm going to present you the work I have been doing these past 2 years. So basically, we added the temporal dimension to the study of ecological interactions. So I will basically just justify why to add this temporal variability to ecological interactions, and then present you to several cases studied of how this can improve our understanding on communities, and then some strokes of things that are going on right now about what to do beyond just characterizing how interactions may vary through time. So why time variance? So, okay, right at the beginning, I'm very happy to be here because I'm able to write down equations. It's something that I cannot always do working with ecologists. So our working system basically are this set of differential equations. They are called the Lotka-Volterra equations that basically describe the growth of the abundance of a species I. That we think it's going to depend on R, that is the intrinsic growth that species would have isolated, let's say, and then plus the effect of the other species that have in its growth. And is this matrix A what is called the interactions matrix, and is the thing that we are interested in. To be more precise, the way in which we define interactions are like the direct effect of one species J in the abundance, in the species I per capita growth rate, without other species held constant. And I say this because sometimes in ecology we study also visitation networks, for example, that are not exactly interactions. So these are our interactions. And usually we are used to encode these interactions in one matrix A. So it's something that is fixed through time. And given as data set, a time series, with some inference procedure, we will be able to parameterize, to fit this model and obtain these parameters. But actually, our question is how and why would this network actually vary? Is this a common, is this the assumption that it's not time varying? Is it good?
this. Okay.
Okay. Green light.
Yeah.
Okay. Okay, so it's now working. Yeah.
Yes. It's almost completely. Yeah.
Okay. What I was saying is that it's clear that if you compare these two scenarios, the ways in which the bird or the plants are going to interact are going to be very different, and these kind of events happened every year. Another example is this one with a pollinator network. So if you just see the time aggregated network, you may think that species, the flower 1 and 2 are sharing a pollinator that is species, that is species 3. So they are going to let's say, like, compete for the attention of that pollinator. But then if you actually see the temporal co-occurrence of these species, you see that actually the flower 1 and 2 do not bloom at the same time. So they actually are not competing for the attention of that pollinator. And during the last, let's say, 10 years, it has been some developments about trying to infer these interactions and see how they would affect coexistence. Because at the end of the day, the ways we have seen empirically in these studies that the ways in which the interactions are going to vary are like everything we can imagine. So links can appear, disappear, they can change their sign, weights, and the same with nodes, the species. They can also go and left. And you may say, okay, so if this is so important and critical, why it has not been studied yet? Well, because there are some challenges to overcome to study this. The first of it is that we need very good data in order to get these networks. And the way in which we get them, so the network inference, is per se an open problem in ecology, how to, from a temporal series of data, you obtain your parameters. I think that Juan and his student knows about this problem. And then finally, we also need to adapt the theoretical tools that we have for time aggregated network to include this temporal dimension. So in order to overcome these challenges, we have this case study in Doñana, where my colleagues has been from the last almost 10 years sampling continuously several sites with several communities. One of that community is wild bees, and the other is one of annual plants. Bear with me. We are not studying pollination networks, okay? They are communities, but they are independent studies. And the good thing is that we have obtained almost 30,000 data points. So we think that with this rich data set, we will be able to infer this temporality of interactions. And our proxy, it's going to be rainfall. Because we have talked about the phenology, so when an insect and a flower blooms. But another key aspect of temporal variability in ecology is the one that is induced by the environment. And this data set, they have a main environmental driver that is rainfall. So our working hypothesis is that this rainfall is going to affect how species parameters are going to evolve through time. So it's going to change these parameters. Basically, we have a drought period over the last years and then some other fluctuations in rainfall. And how we are going to do this? So basically, this is the classical approach. It's, as I have told you, we model the abundance chains. Here we have a discrete version of the model, but it's on the core is the same. So we have our R and our interactions. So with all these data in several locations and whatever, we would create this matrix, this time aggregated matrix plus vector of intrinsic growth rates of R's. But now for us, the story is a little bit different. We are going to add this time variability in species parameters in this way. So it's the easiest way because it's a linear approximation, but it works pretty well with the environmental parameters that we are working on. So now the intrinsic growth rate is going to be a baseline growth rate plus a linear dependence with our environmental variable that is this theta of t. So it has so now the rainfall has a direct effect on the intrinsic growth rate, and the same is added here for the interactions. So now our interaction matrix is going to be a baseline A matrix plus a B matrix that is multiplied by the rainfall value that we would have each year. And with this framework, we can obtain for each year one different interaction matrix and one different set of intrinsic growth rate vectors. So now our first question is to characterize how these vectors and these matrices are varying through time. And then also to study the consequences of this variation to coexistence and stability and these measurements that theoretical ecologists worry about. Did we overcome the challenges? Well, we think that we can humbly say yes, in the sense that we do have a rich data set with a lot of data points that can significantly fit the model. The way in which we have fit it is with GLME, that stands for generalized linear mix effect. It's not the best one. It's not Bayesian. We are working on also using a Bayesian approach, but the inference and the prediction is pretty good. So, and then regarding the theoretical tools, we have well, not made up, but we have we are going to I'm going to present you now some metrics that we think are ecologically meaningful to characterize the interactions, and then the structural stability approach to see how the time affect coexistence. So with the characterization, the first thing that we say is, okay, maybe since now our matrix of interactions is the sum of these two matrices, if matrix B is very, very small, then the environmental effect is going to be very, very small, and almost all the matrices are going to be the same. So we measured temporality. That basically is a metric that tell us how different networks are through time. And we, well, the more different they are, the biggest this number. So at least we know that these values here in B are big enough to produce change time to time in the interaction network. So the networks are different. And now the second step is to see how different they are. So in order to do that, we measured two very important characteristics of interaction matrices in ecology. One of them is looking at the diagonal of the matrices. The diagonal, it's called intraspecific interactions, and basically measures the self-limitation effect that one species has in itself, in the sense that if a species limited themselves more than other species, then coexistence is predicted to appear. But if other species have higher effects than the species itself, then chances are that that species is going to become extinct. So we measure that using a measure called intraspecific dominance, whose values are high, which means that we have this self-limiting effect just during years in which the rainfall anomaly was almost the same as so the rainfall anomaly was small. But as we go to years in which we have drought or the rainfall anomaly is very big, we lose this stability effect that the intraspecific dominance would give us. So just studying the interaction through time, we see that when we have rainfall anomalies very, very negative, then that lessens the stability effect that we would obtain with high self-regulation. Then we also looked at the off-diagonal elements, basically what we would think as interactions, and that are these terms here. And we saw a very curious thing. This is for the BE dataset. So in drought periods, the interspecific interactions that is the biggest is facilitation, so just so positive interaction, and the other way around when we do have more rainfall. And actually, this might seem a little bit counterintuitive in the sense that, okay, so facilitation actually promotes coexistence, and we are seeing it in the harshest of the years, in years when we have drought. So even though this is counterintuitive, this is completely coherent with some ecological hypothesis that has been studied for plants, and this is the first time that we see it on bees. And that mechanism, it's called the stress gradient hypothesis. Oops. So basically, in my non-ecologist mind, what it says is that, okay, when the environment is very harsh, species do not have enough energy to compete for themselves. So at least they are with facilitative interactions. And when we do have rain, and when we have rain, species can grow, then they can compete. And this is the explanation to this apparent counterintuitive trend of these interactions. We do also have temporal variability in the intrinsic growth rates, but I'm not going to focus a lot on that, just to let you know that there are a lot of context dependency and also spatial variability. These are all the species, and the gray lines are sites. So depending on the sites the species is, the intrinsic growth rate can be even with opposite sign. So there are a lot of special contingencies going on. And okay, so with this case study, we can say we have some conclusions that basically is that interactions do vary through time in strength and size, and then that this variation actually has an ecological coherent explanation. So we were pretty happy. And beyond this characterization, actually what we have is a model. So this model, actually, we do have all the parameters except the rainfall, and we always use the empirical rainfall, the historical rainfall. But we can actually, well, but we can actually check other rainfall regimes, other time series of rainfall, to see how the species are going to coexist or not in these different scenarios. So we simulate actually a scenario with constant rainfall. So in that case, it's actually not time varying. Another with increasing rainfall, decreasing, and then this one that for me is the most interesting. This is a fluctuating regime. That is something similar on what is going on. And basically, depending on the data set, we obtain different results. But basically, the results were also coherent with the type of data set we were working on for the plants. Oh, well, and these graphs are the Shannon index that basically measures it's like a Jaccard index. So the higher the index, the more diversity is in our system, in the sense that more species are coexistent, and then the coexistence is like homogeneous, in the sense that we do not have one species with 100 individuals and the other one with 2 or 3. They are all more or less equal. And then if we just have one species that has outcompeted the rest, or just zero species because the system has just died, then we will have a zero. And we see that for some in silico experiment, depending on the rainfall regime, we start with high Shannon diversity, but then we go down, except for this varying regime and strange enough, also the constant one. And then for the bees, what we saw that was critical for them was more rainfall, enough. And this is for simulations. And then another thing that we were also curious about is to look at one thing that is called structural stability, that allows us to add this temporal dimension in the studies. So basically, when we study dynamical systems, we have one set of parameters that is fixed, and we study the dynamical properties of the variables of the systems, in this case, the abundance of the species. But what about, instead of studying that particular instance of our system, what if we study all the possible variations that these parameters can have? So instead of asking, can with this particular set of parameters our species coexist, we can ask, okay, how big is the variability that the system can withstand without any species going extinct? So it's like kind of sensitivity analysis. So we are interested in, for example, if these are species parameters in all this area in which species are going to coexist together. We will call this space feasibility domain. It's just ecology jargon, but basically in this space, we are interested in this region in which we have positive abundance of species, and not in these others in which we will have a system with a subset of species. And the cool thing of this approach actually is that the properties, the shape and size of these regions is completely determined by the interactions that are going on. And then whether we are exactly indeed in that region or no is going to be determined by the intrinsic growth rate. And the reason of this is a mathematical one. Basically, this is our, now we go to the Lotka-Volterra model again. This is our model. It works the same with the addition of time variation. But we have this model. We are interested in these kind of solutions, in the stationary solutions. So basically, resolving this set of equations is basically resolving this. But instead of resolving this, we are actually going to see this equation in a kind of geometrical way. So here, what we are actually saying is that the intrinsic growth vector R can be decomposed as the sum of the column vectors of our matrix of interactions multiplied by this n star that would be the density in the equilibrium. And what we are interested is in having all these coefficients, the n star positive. That would mean that all species are coexisting because they have non-zero abundances. So actually, this mathematically defines a cone or a complex hull of all the vectors that can be decomposed in this way. And that's why I say that the interactions and the growth rate determine the feasibility domain. If we vary interactions, we are actually varying this angle, so the size of the feasibility domain. And even if we allow for positive interactions, this size can become very, very big. And then if we vary the growth rate, then we are going to end up in different regions of the feasibility domain, because we would need different n star coefficients to decompose this vector. And if we allow the interactions and the intrinsic growth rate to vary through time, then what we are doing is to move in this space. So sometimes we will end up in a feasible region, but sometimes we will go outside this region. That will be with 2 species. With 3 species, this region is in 3 dimensions, so this is like a cone. If we project it in the unit sphere, with more than 3 dimensions, we of course cannot see it, even though some theoretical physicists will say they can, which you cannot. But at least we can perform the multidimensional integral. So we can measure the size of this region. And of course, the bigger the better, in the sense that it will withstand more variation. And we got a pretty also counterintuitive result, in the sense that we see that with more rainfall anomalies, actually the size of this region, that we can also be called, we can think about it as the coexistence opportunities. So the size is going to be bigger than with more normal rainfall anomalies. So now here we had one result that at the beginning we were not able to explain. But then, since we have actually all the matrices of interactions, we see that in this region of drought, we have more facilitation. And mathematically, we have seen that more facilitation means that this region, this feasible region, is going to be bigger. So actually, this result is completely coherent with the mechanism that we saw that is operating in this system. And then when we have more normal anomalies, you are going to have more competition. That what does is to shrink the size of the feasibility domain. So this interaction rearrangement can explain this increase during drought of coexistence opportunities. What we can also do is to see where our community is in this space. And in particular, we are interested in see the distances between this vector to the borders of the regions, because if it goes out, that means that some species are going to have a zero abundance. And what we see actually is that irrespectively of the rainfall anomaly, this distance is more or less constant, but with a lot of variability. So that means that the interplay of variation of the size of the feasibility domain, but also the movement of the R vector, at the end of the day, give us a certain constant level of stability. And that, interpreted in a more common language, basically means that, okay, it's pretty good that with this big rainfall anomaly, we have a big coexistence opportunities. But if our vector of intrinsic growth rate is not inside the feasibility domain, or if it's very near to the border, then it doesn't matter how big it is. The species are going to become extinct. And so that's what I called that the species need to be able to profit of these big feasibility domains. And then the last part that I want you to present is a working paper. That is the thing that I'm been talking to you, Manuel. And he said, okay, we have a set of interactions, a set of intrinsic growth rates, and now all these are varying through time. And actually, this in the long term, what is going to affect is how the community is going to be assembled, in the sense that one particular set of these parameters can tell us the story that the community can follow if we allow nodes to invade and to enter or not the community. This is called, so the way in which we study this in ecology is called permanence theory. And what we do to study this assembly of communities is another kind of graph of network, but this is called the invasion graph. So basically, the nodes here are subcommunities. For example, this is community with a species 7. This is community of a species 2 and 7. And a link means that species 2 can invade and retain and survive there. And what we are interested is in see how many paths can lead to a final community in which all the species are coexistent. As you see, coexistence is such an important thing in theoretical ecology. But now, since things are varying through time, we actually do have two dynamics, and this is valid for any system, not only ecology, in the sense that we have the dynamic of our variables, in this case, species abundances, but then we also have the dynamics of the the attractor of the parameters that define an attractor, that is the intrinsic growth rate and the interactions. But then those parameters, the dynamics of these parameters, in turn determines the dynamics of the variables of the abundances. So it's a continuous wheel of dynamics that whose effects cascade in other dynamics. So what we have seen is that the movement of our community throughout this is with 3 species, this is a toy example, in this feasibility domain actually changes the ways in which the community can be assembled. Here, for example, you have all possible subcommunities and all possible paths that arrives to the final full coexistent community. But as we move, we can lose nodes, so we can lose subcommunities, and we can also lose links through the assembly graph. And just as a preliminary result, these are the graphs for every year in, well, actually the 8th year is missing. Well, for our communities, and we see that these graphs are completely different from one another. And now we are trying to characterize not the interaction metrics, but the relationship between the interaction metrics and these invasion graphs. And since my voice is finishing, so is this presentation. So the conclusions is that, okay, so this work is I know that it's pretty complex, as in half an hour I cannot properly explain it to you. But what we have been seeing is that it's common for several types of organisms, which is something that in ecology is not usually the case, in the sense that there are not so many universal properties of communities. And then our 2 key messages is that with this framework, we obtain a working model, and we can simulate other scenarios in this model. And we can also create one ecological story about coexistence opportunities and coexistence mechanisms. And well, this has been my postdoc work, but with, of course, with my collaborators, especially my PI is Oscar Godoy. I'm a group of mathematicians at the University of Seville. And then this summer, I had the idea to apply to Complexity 72 hours to, I don't know, to just transmit my love of ecology to other students. And I had the opportunity to work with Lisa and Hun in this project. So actually, they can, if you are curious, they ask them, because they can also explain you these things. And thank you very much. These are some works. And
no, thank you, Violeta. So any questions in the audience?
Thanks. Hola. Thanks, Violeta, for a very nice talk. I'm wondering about, well, if you can tell us something about the time scale, because there's a time scale for the dynamics of the species and then a time scale for the perturbation, if you want. So can you infer what's the time scale for each of them? Or how did you manage to deal with these things?
Give me the microphone because my voice is almost over. No, this is a key question actually, and I always get that question when I present this work. No, this is a knowledge that you have to know in advance. And we actually choose these study systems, the wild bees and the plants, because they are annual species. So we knew that the time scale was a year. Of course, we simplified a little bit things because with plants you also have the seed bank, so that are seeds that remain like dormant several years. But it's almost like the community is reset, and the abundances of 1 year, we are confident enough to say that depends only on the abundances of last year. And the same with the environmental driver. The seasonality in these sites is very sharp. So we need, of course, if we wanted to study trees, we would have we would have need like a way longer data set. Yeah. No.
And two questions for the first part. The first, I mean, they are related, but the first question is, when you speak about the rainfall, that can be negative, so it's
anomaly, rainfall anomaly.
rainfall anomaly, that's the annual anomaly, right?
Yeah.
But it could be, I mean, the distribution of the rainfall, let's say, along the year could be important also. I mean,
Yeah.
I mean, for instance, for plants, if it doesn't rain some moment, but then rains later, I mean, the anomaly would be small in the, I mean, if you compute it annually, but could be relevant.
Yeah.
I have a second question.
Okay, yeah, I will ask you first this one. Yeah, the rainfall was the cumulative rainfall through the year, and I mean in the photo of the stork, there you clearly see that actually there are huge variability throughout the year in rainfall, which of course is going to be super important for the plants and the bees, in the sense that if it rains a lot in the wrong time, then especially the nests of the bees are going to be flooded and the bees are going to be dead. We also simulate some of this variability that complicated the model. So at the end of the day, the prediction of the observed versus the observed versus predicted abundances that the model can get was pretty good with just the cumulative. So for these general questions, we just remained in the cumulative rainfall. But yes, it's super important, but the model performs pretty well with just the cumulative rainfall. Yeah, that could be something that we could explore more.
Okay. And the second question is that as you are studying phenology in plants and insects, I mean, many classical studies that study phenology, I mean, consider models in which you compute quantities like degree days or something like that. So temperature, and I mean, from some minimal temperature, I mean, which is the difference? So temperature is not relevant in your studies. I mean, just with rainfall, I mean, you are able to capture all the variability.
Okay, we did not choose temperature because we wanted a common driver for both systems. The temperature would be very important for the bees and not that much for the plants. But for example, I did not try to feed my bee data set with temperature. Would be something interesting to say. But first, what I have been doing for other data sets is in which we do not know so well the main environmental driver. is that I have done a PCOA of all the environmental variables, and then I take the first agent vector. I don't know. I think that they might be correlated, but it's something that I have not done. That's cool. Anti-correlated, but I don't. But even though correlated or anti-correlated, it will have the same information. So I don't know how critical it would be to use both or just the temperature. Yep, cool. I will tell that to the entomologists.
I have two questions. One is I don't really understand the nature of the data set because you are talking about plants and bees, but you are written the notable terra. So how many species do you have in each data set? And you have bees and something else, or plants and something else, or what do you really measure? What is the data set?
Okay, so for the wild bees, it's not here anyway. Okay, so we have 5 wild bees because we choose the ones that were present in every site every year, and then we have 7 annual plants.
Okay, so you don't consider just bees or just plants? You
Yes.
don't consider bees and beetles and
No.
okay.
Also because I mean, traditionally it has been studied more. Predator-prey food webs networks, and we wanted to study what are called intra-guild networks. And then for the annual plants, only plants were sampled, not its pollinators in that case. For the wild bees, we do have some information about the plants, but not that much in order to be sure that we could infer also their dynamics. So yes, it's an intra-guild community.
And my second question probably is related to your answer, but in your model, you assume that the rainfall affects all the zero abundance growth rate in the same way, and the matrix of interaction is affected. So you multiply the rain towards a fixed matrix. So the rain is affecting all the interactions equally and all the growth rates equally. Is this just simplicity, or there is any reason that justifying this, or?
No, it's just simplicity because, I mean, even though our number of data points was big, we couldn't fit any more complicated form. Like I wanted to do a sigmoid. So in order to have some saturation point or even some mode function. So because sometimes, for example, the dependence of R and temperature. So you have like a sweet temperature point in which your growth is the highest, and then with very high or very low temperature, your growth just plumped. But that would mean to add more parameters to fit, and we were not able to do that. So, for example, in the simulations, we couldn't put any rainfall value. We were just constrained to the values that were empirically true during our time. So it was like an interpolation. So yes, of course. It's a line. So if you actually go very, very high in rainfall, that is not going to work. So yes, for simplicity. Yeah.
Thank you.
Thank you, Violeta. I wanted to ask you about the fit. I was wondering because there are systems like this with high dimensionality in which you can get very good fits, and despite that, the predictions then go really wrong because you are overfitting the data. So have you checked that, and you also mentioned that you're planning to do Bayesian statistics. What are the approaches you are trying to avoid these problems that all people that try to infer ecological networks have?
Yeah. So basically for me, so first I did a model selection So I try to increase complexity, but without compromising overfit. Actually, I would have to explain this. I would have to, okay. So basically the model that we choose is this one, that is way better than other more simple model and not that complicated. This is the Akaika information criterion, but actually the image that I wanted to show you is this one. So basically here you have the observed growth rates and the predicted growth rate of our model for all our species. So basically this was the image that more, let's say, convinced me that the model were doing well. Of course, you have these values that, so these tendencies that tells you that actually for very little grow, it's not performing that good. But looking at other works in ecology, this is pretty good. I'm not very happy with it. That's why I'm trying to do Bayesian statistic instead of this generalized linear mixed model that basically is a. I mean, it's very complicated, but it's just like a minimum squared procedure, but very complicated. And yes, so this is the image that for which you can judge yourself the validity of the model. Then it's true that since we were able to obtain some ecological explanation of the networks that had sense, we were confident to say, okay, we are not obtaining nonsense variation of interactions. We are obtaining things that has been explained in other words by other means. But yeah, the fitting is for me is the weakness of all this framework, because you need a lot of data, and then you have to trust your inference model. Yeah.
Thank you, Violeta. I have two questions also. First one is, correct me if I'm wrong, various of the metrics you have shown to, let's say, study the stability of the communities in there. Like, if I'm right, many of them are like dealing with the relative abundances of species in there, right? I mean, the Shannon index, for instance, you told us that, okay. And I was wondering, because these counterintuitive results you showed that in harsher conditions, there were like more stability for some cases. Have you checked also the absolute abundances of the species, not only the relative, to check, perhaps there are more stable states in there, but there are less in numbers, so fluctuations may kill all of the entirety of the system.
Okay, I think you are thinking in the stability sense to eigenvalues and this work or may, but this is another kind of stability. So for me, it's not only important the size of this region in which you can have coexistence, that is this right part, and is the one of, I said, the contraintuitive results, but it's also very important, that is only determined by the interactions, but it's also very important the vector of intrinsic growth rate and the interplay between how big and the shape of this region and where my community is. And this is the left graph. And if we take these two things into account, then the level of what we call structural stability actually do not vary that much.
So my second question was related to eigenvalues, in fact, because let's say this feasibility domain was like the region in which there are stationary states, but not what of those states are stable or not, right? In the sense of eigenvalues.
Yes, I mean, what we only care about is if in the long term, and by long term, I mean, if we maintain fixed these parameters for long enough, whether the final state is going to have positive abundances for all the species. But we do not care at all about whether that state is going to be stable or unstable in the sense of having a negative or positive.
But this unstable is not the final state.
Is
Right.
what?
It is, the state is unstable. There are no chances that that's the final state of the system.
I mean, it's never going to be in that state, even if it's stable, because you do not have enough, because I mean, this system is at non-equilibrium. So you do not have enough time to get to that fixed point, because in that time, your parameters are going to change, and that is going to influence your dynamics of the abundances. So the abundances now, they are going to go to another fixed point, and before they reach it, they are going to change and go to another. They're going to go back and forth. So,
but what I mean, sorry, is that.
okay, sorry.
No, sorry, no, that was super right. But I mean, like, I don't mean that they will reach that final state, but they will sometimes even approach that state if that's very unstable, right?
Right, it can happen. Yes.
Yeah. Okay. That's my only question. Right. Thanks.
Okay.
More question? No. Yes. Thank you again.
Sí, gracias. Es muy complicado de explicar, pero bueno. Ups. No